we're going to solve the inequality 3x to the fourth plus 10x less than or equal to 11x cubed plus 4. To solve this type of inequality, which is a polynomial inequality, you have to get the polynomial on one side of the inequality and 0 on the other side. So I'm going to put the polynomial on the left side and all the terms, if you want, on the left side, and then 0 on the right. Okay, so that's the first step you usually do. Okay, so we have the polynomial 3x to the 4 plus 10x less than or equal to 11x cubed plus 4. So I would subtract 11x cubed on both sides, and I'll also subtract 4 on both sides of the inequality. So doing so would give me 3x to the fourth minus 11x cubed plus 10x minus 4 less than or equal to 0. Okay, and so our p of x in this example, or our polynomial function, is that there. Alright, so the second step when solving a polynomial inequality is to solve the related polynomial equation, p of x equal to 0. Alright, to do so, we have to find the zeros, or real zeros, of this polynomial. Okay. In this case, it's not easy to see how to factor this, and therefore we're going to rely on some examples of some theorems that we've probably seen already, such as the possible rational zero test and Descartes' rule of signs. So let's look at Descartes' rule of signs real quick, just to give us an idea of what type, if we have any positive or real zeros possibly. Okay, so once again, basically you examine p of x and see how many sign variations or sign changes the polynomial has. Okay, and so let's rewrite this polynomial and see the sign changes. So we see it went from a positive coefficient to a negative coefficient, so that's one sign change. And then it went from a negative 11 to a positive 10, so that's another sign change. And then positive 10 to a negative 4, that's another sign change. So there's 3 sign changes. So Descartes' rule of signs tells us there's going to be either 3 or 1 positive real solution. I'm going to just say 0. Okay. Now we could do that again, except this time we, instead of looking at p of x, it's the sign variation of p of x, we look at the sign variation of p of negative x. And we could see that's plugging in the negative x into our polynomial and simplifying it. And we see we get a positive 3x to the fourth. The negative will pop out of the x cubed term there. And so we get a negative and negative, which makes this positive 11x cubed. And then we get a negative 10x minus 4. And you can see that the first coefficient of 3 to the next coefficient, 3 and 11, both it did not change sign. So they're both positive, but it does change sign from a positive 11 to a negative 10. But the negative 10 to negative 4 didn't change signs. So we know that there is one negative real zero. Okay, so now we're going to use what's called what I like to call the possible rational zeros theorem. And basically, which means we're looking for fractions of the form p over q, rational numbers, where p is a factor of the constant term. which in this case is -4, and q is a factor of the leading coefficient. Which in this case is 3. Okay, so what we do first is figure out the factors of -4, which would be plus or minus 1, plus or minus 2, plus or minus 3, not 3, but 4, excuse me. And then q, the possible factors of q is plus or minus 1 and plus or minus 3. Okay, because those are the factors of 3. All right, and then what we do is form the possible rational zeros, which is p over q, where we're going to take each p and divide by each factor of q. So first, we'll list the plus or minus 1 divided by plus or minus 1, which is just plus or minus 1, plus or minus 2 divided by plus or minus 1 is just plus or minus 2, and then plus or minus 4 divided by plus or minus 1 is 4. Now we do the same thing, but this time divide by plus or minus 3. So we get plus or minus 1/3, plus or minus 2/3, plus or minus 4/3. And this tells us the possible rational zeros. So if we have any zero that's a rational number, it has to be part of this list here. And from Descartes' rule of signs, we know we have one negative real zero, and so we're guaranteed that. Now, whether it's a rational number or not, that remains to be shown. And so I'm gonna just, since I know we have at least one real zero, negative real zero, I'm gonna start with the negative number. So I'm gonna take -1. I'm gonna use synthetic division here. So synthetic division. So we get 3, -11, 10, and -4, and then this will tell us if -1 is 0 or not, if we get a remainder of 0. And so we bring down the 3, so we get -1 times 3, which is -3, -11 plus -3 is -14, and I'm going to make a mistake here because I forgot our polynomial here is missing an x squared. So I need to rewrite this or give some space here for the x squared term, which in this case we could think of it as 0. So don't forget that, like I was about to do. All right, so we get -14. So -1 times a -14 is positive 14. Atom, we get positive 14. Now -1 times a positive 14 gives us a -14. 10 plus -14 is -4. And then we have a -1 times -4, which is positive 4. So we get 0. That's good news because that tells us that our polynomial, our -1 is a 0, and p of x now factors as x plus 1 times the quotient. Okay, in other words, in this case, it would be 3x cubed minus 14x plus 14 minus, 3x cubed minus 14x squared minus 14x plus 14x minus 4. Okay. So we actually found the one negative real zero, which happens to be a rational number, -1. Okay, so we could do synthetic division again, but instead of using the coefficients of the original polynomial p of x, we'll use the coefficients of, say, this other polynomial, the quotient. So let's try 1/3. All right, so we get 3, -14, positive 14, and -4. And the reason why I'm using 1/3 is because it's on my rational zero list, and I'm just trying any number here. I could try 1, I could try 2, something like that. You don't have to go in order. And not only that, you should note that the quotient has the same leading coefficient and the same constant term, and so the list is the same. In other words, if you perform the rational zero term again, then we would get the same list. Okay, so I'm gonna try 1/3 now. Bring down 3, we get 1/3 times 3, which is 1. Then we get negative 13. Then 1/3 times a negative 13, which is a negative 13 over 3. And then 14, right, minus 13 over 3. Let's find a common denominator, which would be 3. So top and bottom by 3 here. So we get, what is that, 30, 40, 42. 42 over 3 minus 13 over 3, which gives us negative 20, what is that, negative 20? Take a calculator here and try that. So I don't make no error. Okay. Let's see, 42 minus 13 gives us 29. So negative 20, a positive 29 over 3. Okay, so let's see here. Double check my work here. Alright, so 29 over 3. Okay, and then we multiply. Clearly this is not going to give us 0, but 1/3 times 29 over 3 is 29 over 9. And this is definitely not 0, so I'm not even going to bother to check. Alright, let's try 2/3. And plug in our same coefficients here. So 3, negative 14, 14, and negative 4. Alright, so bring down the 3. 2/3 times 3 is 2. Add them, we get negative 12. 2/3 times a negative 12. Well, 3 goes to negative 12 4 times. So we get negative 4 times 2, which is negative 8. So 14 plus negative 8 is positive 6. And then 2/3 times 6, well, 3 goes into 6 twice. So 2 times 2 is 4. And so negative 4 times 4, plus 4 is 0, which is good. That tells us that 2/3 is a 0. And not only that, it tells us that p of x factors as x plus 1 times x minus 2/3 times the quotient of this new synthetic division, which would give us x squared, or not x squared, but 3x squared minus 12x plus 6. Okay, and so now, well, I could actually continue factoring. I notice these all have a 3 in common, so let's factor out a 3. So that's 3 times x plus 1 times x minus 2/3 times x squared minus 4x, and then plus 2. Alright, so well, we're pretty much there. We just need to find the zeros of this part here. And so we know that 3x plus 1, we could use the 0 factor property, right? That factor has to be 0, or x minus 2/3 has to be 0, which we already know those zeros. And then x squared minus 4x plus 2 has to be 0. Okay, so x squared minus 4x plus 2 doesn't factor over the integers, meaning I can't find integers or whole numbers that will multiply to give me 2 and add up to negative 4. But we know, of course, we could use quadratic formula. So the first equation, of course, that tells us x equals negative 1, and then x equals 2/3, the other one, and then now we just use quadratic formula to find the solutions to x squared minus 4x plus 2. And so to do that, we're going to use the quadratic formula. So minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So b in this case is a negative 4, so we have a negative times a negative 4 plus or minus the square root of negative 4 squared minus 4 times negative 4 times 2. And then divide that by 2 times 1. Alright, simplifying this, we get a positive 4 plus or minus the square root of 16. I think I'm not sure why I plugged a 4 here. I take that back. That's not a 4 because it's AC. So AC, A is 1. So that's a 1 there. All right, so we have -4 squared, so which is 16, and then minus 4 times 1 times 2 is -8, all over 2 times 1, which is 2. All right, so then simplifying that there, we get 4 plus or minus the square root of 8 over 2, which is 4 plus or minus, and then if I reduce or simplify the square root, that's going to give us square root 4 times square root 2, so that's going to be 2 radical 2 over 2, and then of course I could think of this as factoring out a 2, which leaves me with just 2 plus root 2, and then or 2 minus root 2 as my solutions there. Since these are irrational numbers, it's kind of hard to figure out where they place where they would place on the number line. This is approximately, I'm going to take this up to 2 decimal places, about 3.41. So it's about 3.41 to the hundredths place. And then the next one here, 2 minus root 2, that's about, let's see, 0.59. All right, and we need those values because since we have our zeros now, -1 2/3, and 2 plus root 2 and 2 minus root 2, the next step, step 3, is take a number line and break up our number line into the intervals that our zeros create. So we have -1 over here. We have 2 minus root 2, and that would be pretty close to 2/3. And then we would have 2 root 2. And so we have 1, 2, 3, 4, 5 intervals. We have the interval from -infinity to -1, the interval between -1 and 2 minus root 2, and then the interval from 2 minus root 2 to 2/3, and then the interval from between 2/3 and 2 plus root 2, and then 2 plus root 2 all the way to infinity. Okay, so let's go ahead and take a test point. I'm going to take a test point of, say, -2 over here, between -1 and 2 minus root 2. So remember, -1, between those numbers, there's going to be somewhere in there 0 is. That's probably the best one to choose there. So we have a test value, -2, 0, and then we'll take a test value of, say, well, 2/3 is about 0.67. So, and then 2 minus root 2 is 0.59. So let's go ahead and choose 0.6. So we'll choose 0.6 there. And then we'll choose something between 2/3 and 2 plus root 2. 3 would be a good choice there. 3. And then something larger than 2 plus root 2. So 2 plus root 2 is about 3.41. So let's go ahead and check 3.41. Let's take the 4. Kind of got distracted there. 4. Okay, so those are our test values. And we know that at -1 we have 0. At 2 minus root 2 we have 0. And then 2/3 we have 0. And then at 2 plus root 2 we have a 0. Now we just got to figure out the signs in each one of those intervals. So what we do is plug in our values into the polynomial. So we have p of -2, which would plug into our original polynomial, which was this guy up here. Okay, so let me just copy that so I can see it, so I don't have to go back and forth. All right, that's our polynomial there. And so we have 3 times -2 to the 4th minus 11 times -2 cubed plus 10 times -2 minus 4. Let me go ahead and plug that into a calculator here. So we have, so 3 times negative 2 to the 4th, minus 11 times negative 2 to the 3rd, plus 10 times negative 2, and then minus 4. Okay, so we get, if I did that right, double check. All right, so I get 112, so it tells us it's positive there. Do that in a different color. So it's positive here, and the interval from negative infinity to negative 1 is positive. The outputs are positive. Okay, and then between negative 1 and 2 minus root 2, we chose 0, so we have p of 0, which would be 3 times 0 to the 4th minus 11 times 0 cubed plus 10 times 0 minus 4, so we get negative 4. So we know it's negative between negative 1 and 2 minus root 2. And then between 2 minus root 2 and 2/3, we're going to take our value of 0.6. And then we get, let's do that again there. Okay, so we have 3 times 0.6 raised to the 4th power minus 11 times 0.6 raised to the 3rd power plus 10 times 0.6 minus 4. So 3 times 0.6 to the 4th minus 11 times 0.6 to the 3rd power plus 10 times 0.6 minus 4. All right, so we get roughly about 0.0128. It's a positive value, so that means it's going to be positive in the interval from 2 minus root 2 to 2/3. And then now we check 3. So we plug 3 into the equation, or polynomial. So 3 times 3 to the 4th minus 11 times 3 to the 3rd plus 10 times 3 minus 4. Let's see what that spits out there. Okay. 3. Okay. And we get negative 28. So it's negative. And it's pretty clear that it's going to probably pass through the x-axis at from below and then go up at 2 plus root 2. But you would plug in your test value as well. So we're going to plug in 4. But it's 3 times 4 cubed to the 4th minus 11 times 4 to the 3rd power plus 10 times 4 minus 4. And let's see what that equals. All right. So doing the calculation, get about 100 there. So it's clear that it's positive on the interval from 2 plus root 2 to positive infinity. Okay, so well, step 4 is to interpret our table and write the solution set. I'm going to use interval notation, but we're interested in solving the equation where, way back up here, this one here, right? And so that's equivalent to this here. This is equivalent, so we were looking for less than or equal to 0. So we're interested in when the output of p of x is negative or 0. So let's go ahead and look at our chart. So negative or 0, so we can see it's going to be basically this portion here, right? And between here and here, that's what we're interested in because that's the intervals that's going to give us outputs that are less than or equal to 0. All right, so our solution expressed in interval notation is going to be negative, and it's going to be a closed interval, bracket negative 1 to 2 minus root 2, closing bracket, because we need to include the negative 1 and 2 minus root 2 because those values give us 0 and we're interested in less than or equal to 0, right? Okay. Union bracket 2/3 to 2 plus root 2, closing bracket. And if you were to do set builder notations as a set of x such that -1 is less than or equal to x, and x is less than or equal to 2 minus root 2, or 2/3 is less than or equal to x, and x is less than or equal to 2 plus root 2. Okay, so that's the solution set for that inequality. Okay, so let's see how we could have solved this polynomial inequality. 3x to the 4th minus 11x cubed plus 10x minus 4 less than or equal to 0 using the graph. And so we'll use our decimal calculator. And so we have 3x to the 4th minus 11x to the 3rd plus 10x minus 4. And here it's kind of misleading, as you notice when we did this algebraically, we had 3 zeros. We had the zeros -1, 2/3, 2 plus root 2, and 2 minus root 2. But here it looks like it only has three x-intercepts. But if you look really closely here, you can see that there's actually 2 points. So you wouldn't notice that unless you kind of zoomed in just a tad there. And zoom in quite a bit there, you could see that those are the zeros, the 2/3 and the root 2 minus 2 minus root 2. And so you can see there's actually 4 zeros there. Okay, so to solve that inequality, we were looking for when the portion of the graph was below the y-axis. And so zooming in just a tad here, so we can see if we here at the 0, -1, all the way to the 0, 2 minus the square root 2, it's below the x-axis, which means the outputs would be negative. And so that's why we would take the interval from -1 to 2 minus root 2. And then you can see if you zoom in a little bit closer here, that it's actually positive between 2 minus root 2 and 2/3. But then once the graph, it goes, it's above the x-axis, and then after that interval between those two numbers, it falls below. And you can see that there it's below until 2/3 to 2 plus root 2. It's below, and so that means that the outputs are negative, which satisfies the inequality. And then after our other 0, 2 plus root 2, it remains above the x-axis. And if you zoom out, you can see that. And that's how you would solve that inequality using the graph. But you got to be careful with graphs sometimes because they can be a little bit misleading if you don't pay close enough attention. That's it for this video.